describe the main elements and relationships in our system. We can also describe actual system configurations. We want to describe the components in our system. We also want to somehow describe the actual state of our system, and structural modeling supports also these aspects. And structural modeling supports the description of the topology in our system. For this purpose, UML introduces many concepts. So the key concepts are the following. We will go into the details related to classifiers. We will see data types, classes, interfaces, enumerations, and their features such as attributes and operations. And we will discuss also the relationships between the various classifiers, and we will also see compound structures, especially at the second part of the talk today. So the goal of static modeling is to identify data types, classes, interfaces, components, and their relations, and outline participants and their role in the collaborations. And the strength of UML that it provides a rich toolkit, scaling well from basic data modeling to large software components. And it provides diagrams that are easy to overview, and let's say that it is semantically well founded, so it can be used for as an input of code generators. Well, actually, unfortunately, this is not true for all the cases, so be careful when you use UML for code generation. As I mentioned you yesterday, there is a foundational subset of UML that supports this, but there are also parts of the UML standards that are, how to say, not so clear, not so precise. They are defined not so precisely. So let's see the main building blocks. Is everything okay, or? Oh, okay. Should I move to there, or is it good if I talk here? Or should I just show in that picture what I want? Okay. 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 So, what are the building blocks of class diagrams? So, the roots are actually the traditional object-oriented approaches. Please raise your hand. Who is familiar with object-oriented programming? 1, 1.5, 2, 3, 4. Okay. So for those, it might be a little bit boring. So the traditional object-oriented approach relies on object. So we say that the system is built of object, and the objects have their own attributes and operations. And we have to provide the meta model of a concrete system. So we will define a model for that purpose. And in this meta model, we will define classes. A class can be regarded as a template for objects. So a class defines the template for those objects that will be used in your system when it works. And it provides also the attributes, operations, and we will see the visibility and types and so on. And in traditional object-oriented approaches, you try uh, to express some kind of topology in between your objects, and this can be defined, for example, by using generalization, and we can also define abstract. Just for the object, but also for the relations. And we will see, this is called associations, and we will see various properties of these relations. So endpoints can have multiplicity, role, name, navigation, containment, such as aggregation, composition, and we will see also attributes. Attributes can be regarded as binary associations. So, and mainly, just to tell you some best practice, attributes are usually the built-in data types of our system. And in all the other cases, we will see the various representations of the classes. So here we can see 3 classes that are associated to each other, and you can see one representation in this left side, but you can use another kind of representation. So you can put just these elements into this device class, actually. And as you can see, this is just a reference. As here you can see, this is just an association, but you can also denote aggregation, composition. But we will see them in more detail later. So if we start dealing with UML, we have to define classifiers and the concept of classifiers first. This is a very, very abstract concept, actually. So I will give you the definition, but actually it's not so important for the everyday life. It is important to understand how a class diagram works and why it works this way. So a classifier source for the classification of instances, any kind of instances. So it describes set of instances that have the same features. So a classifier also may participate in generalization relationships with other classifiers, and an instance of a specific classifier is also an instance of each of the general classifiers. That this generalization thing we also saw yesterday when we wanted to define the actors in our system. And actually this comes from this object-oriented paradigm, and this is actually defined at this classifier level. And you can also define time conformance of the classifiers, and this conformance relation and conformance rules are are valid for all those elements that we just derived from classifiers. So the type conformance of classifiers is as follows. A classifier conforms to itself. That's quite easy to understand, and to all of its ancestors in the generalization hierarchy. And this is defined at the classifier level. But why I started to talk about this? So if you see this diagram, at the top level we have the classifiers that are every other thing, such as interfaces, signals, data type, class, association, primitive types, and enumerations are related to this classifier. So this is the general concept that tries to capture the basic features and the basic properties of all those elements that you can use in a UML diagram. And that's why it is actually important. And as you can see, this is an abstract class. So you will never use classifier in your model, but all other things that you can use are related to it and inherited from this general concept. So when we go to the classes, the definition of classes is quite similar to classifiers. So it says that a class describes a set of objects that share the same specification of features, constraints, and semantics. So this definition is very similar to the general definition of classifiers. So it just inherited this definition. And class can have structural features that will specify the structure of instances. Such features are attributes and association roles, and we call them properties in general. And classes can have also behavioral features that specify behavior of instances, such as operations, signal receptions, and the main behavior of the classes. And you will see later, we will describe these behaviors, for example, with state machines or activity diagrams in later. So the semantics of classes. So the purpose of a class is to specify a classification of objects and to specify the features that characterize the structure and behavior of those objects. And the objects of this class must contain values for each attribute that is a member of that class. So we define the template in the class as a template, and when we instantiate it and we have an object of this class, then actually we have to fill the attributes of that object, because we defined these attributes that these objects that are of this class must have. And the operations of a class can be invoked with the substitutions of the parameters. And an operation invocation may cause changes in the values of attributes, and it can have also, operation call can result some return values. Here is how we used to denote classes with this classifier symbol with 3 compartments. So here you can see the name of the class that are used to be capitalized, and there are some other rules. They depend on mainly about the modeling tool you use. And there is an attributes compartment. So here you can see the attributes of this mover class, and here you can see the operations that you can invoke on the objects that will be instantiated from this class. And there can be also additional compartments. For example, you can provide constraints and so on with some other compartment in the bottom. And let's continue with interfaces. So now we saw classes, and we can define interfaces for the classes. And an interface declares a set of public features and obligations that constitute a coherent service offered by a classifier. So here in the example, you see that it is actually a class, but you can just implement realize the interface with other classifiers too. And an interface can be regarded as a contract. So any instance of classifier that realizes the interface must fulfill that contract. So here is the implementing class. We denote the interface realization this way. And here is our interface, that is a sensor interface. And it tells us that it has a get sensor data and check sensor functions, operations that you can call. So in the temperature sensor, you have to implement these services and you have to provide these services. There are various data types in UML, and these will be extended by later by SysML. So a data type can be defined as a type whose instances are identified by only their values. So just if you want to represent, for example, numbers, for us in the general case, 5 equals to 5. So we don't care about how and where we produced this number. So numbers, for example, a typical example for data types. But if you have objects actually and that represent something more complex, and actually the existence of an object still represents some information for us, then you will not get this equality. So, for example, regarding people, even though maybe there are some other people that have the same height as me, we are not identical. So we can make difference. So data types just identified by their value. And the data type may contain attributes to support the modeling of structured data types. And here you can see, for example, it's a primitive data type, string, but you can also have some more complex data types. So here we represented a coordinate, XY coordinate, to represent some points in a field, and they have two attributes. And the typical use of data type is to represent the programming language primitive types. So integer, string types are often treated as data types during modeling. And we talked about it so that there is also, we can define enumerations. That is also a kind of classifier. Enumerations can be described as a fixed set of symbolic values represented as a class with values as attributes. And the typical usage of enumerations is to define possible states of the system. And instead of using hardwired string literals and strings, it is often advised to suggested to use enumerations, because then if you have, for example, a code generator, then you can use these symbolic values as it is good for you. And this is not true if you just have many strings and everything coded in strings. And we also have to talk about signals. A signal is a specification of send request instances communicated between objects. So it is related more to the communication, and it can carry data. So also a signal can have some attributes, and this data can be accessed by the classes, and when we use these signals. And the signals can be defined independently of the classifiers handling them. So here is the classifier where we handle this temperature data signal, but it is defined independently. And you will see that these signals, you can use it in other modeling languages. So we will use them tomorrow in the definition of behavioral models. And so another big category and important classifier is the objects. And UML introduced the object diagram to define the objects in our system. So an object can be defined as a cohesive entity instance that have attributes, behavior, state, and identity. And an object can be used to represent real-world things, but also it can represent conceptual entities. But it's important to note that an object is still an abstraction of real-world entities. So this is still one abstract level above the real world that it will represent. So for example, we can have the objects of chairs, but these objects will not represent every property of these chairs, just those properties that are relevant for our system. So it's important to note this. And if you compare classes and objects, actually a class is a design time concept, while objects are used at runtime. And classes define the type of some set of objects. So for example, int is the type of 5. So classes can be regarded as abstract data types plus the operations. And a class specifies both the structure and the behavior of all the objects instantiated from it. And all objects of a class have their own copies of the very same set of typed attributes. And each object has the same set of methods defined by the class. However, for efficiency reasons, sometimes they share code, so you don't copy to all your objects the same code. But from the logical point of view, they all have their own code. I do not know if these concepts are clear to everybody. Okay. And UML uses object diagrams to define the structure and the relationship between objects. So in a traditional object-oriented approach, the system is built of objects with attributes, operations, and concrete values. And the object diagram supports the description of these objects and their relationship. With the help of object diagrams, we are able to specify concrete system configurations, and it can, for example, be used to describe test inputs for a system. And also it can be useful for simulation. And there are various solutions to generate these kind of configurations, for example, from class diagrams, even automatically. And now we know the basic classifiers. We also have to talk about their attributes and operations and how we define them. So for this purpose, I will show you a small example. And we will store personal data such as names, birth date, and we will provide operations So, for example, we can change the name of the person that will modify the object, or we will calculate the age of the person that doesn't modify the object. And how can we do this? Here you can see a person class with all the attributes and operations. And you can see the function, the operation to change the names, and you can see that we can calculate the age that will not modify the object. So I want to describe you what attributes are. So attributes are structural features of classifiers, member variables or fields of the classifiers. And attributes have their name that are specific type. They are exposed according to some visibility. They can have multiplicity, default value. And this is the notation that is introduced in UML for the definition of attributes. What are the elements? So at first you see the visibility. At first you define the visibility of the attribute. It can be public. That means that anybody can access this attribute. You and me too. It can be private. That means that only instances of the same class can access this attribute. It can be protected. That means that descendants of the class. And it can have the package visibility. This means that classes in the same package will be able to access this attribute. And we just use these signs to depict this visibility properties. After that, you can define that if the property is derived, that means that we will not store this attribute, but we will compute it all the time when somebody wants to access it. Then comes the name of the attribute. Then we define the type of the classifier actually, and then we can define the multiplicity of the attribute that can be exactly 1. That is default if not specified. It can be exactly n, it can be between n and m, or it can be any. And the default value is an expression that evaluates to the default, that defines the default value of the attribute. And there, at the end, you can also use some modifiers that will modify the attribute, the semantics of the attribute. For example, an attribute can be read-only. It can be a proper subset of another attribute. An attribute can be a union of its subsets of other attributes, and we can also redefine inherited attributes with these modifiers. So, and also we can express that an attribute if it is ordered, especially if this is interesting for multi-valued attributes, and this can also tell us something about some implementation details. For example, if we would like to implement it as an array, and we can also tell if an attribute is unique. So there are no duplicates in this attribute. So let's see how it works with our example. So as I mentioned, we will store data about people in a database. There will be a unique generated database key string that shouldn't tampered with. We will store the birth date, and there will be an attribute of the age, but it will be calculated from birth date and the actual year. And there will be also data security field that may have been modified by subclasses if these subclasses extend and add new attributes to our class. And we will also store first names, where the rule is that at least one forename order is important. One name may appear at most once. There we build the attribute of last names. At least one surname order is important. And the name is calculated from the first and last names. And because for a name, it cannot be always decided whether it is a first or last name, as this is read-only. This is especially true in Brazil, because I saw that you had very, very complex names. In Hungary, actually, it's much more easier. But here, everybody has 4 names, and I never know which name is for what purpose. So that is quite relevant here. And we also want to store email addresses. We will store the personal email addresses. Person can have any number of personal email addresses, but one address may appear only once. Person has also corporate email addresses, any number, and one address may appear only once. And the email addresses attribute is the union of the two above. And for an address, it cannot be determined whether it is personal or corporate, thus this is read only. So what we will see is the visibility, name, type, and how we can define derived attributes. We will see some examples for multiplicity ordering, for read-only and unique attributes, and derived unions. So let's go back to our simple class person, but it has now some more fields, some more attributes. So at the top, you can see a unique generated database key that shouldn't be tampered with. So this will be private. So do you have a question? Do you have a question? Okay. So the attribute is of birth is a date, and the age is calculated from the birth date and the actual year. So it is a derived feature, a derived attribute. So we will not store it in our memory, but we will compute it again and again, and this way we can have always the actual value, the current value. I just want to ask you, can you tell me an example when you would avoid of this kind of calculation of derived attribute and you would just store instead? Can you tell me something? On the last row? Somebody? So let's just take an example. If, for example, for now it's very easy. You just subtract 2 numbers and that's all. But if it is something really complicated, computation, and you have to use it often, then you will just store instead of doing these very, very complex calculations. So sometimes sometimes the life actually overrides the rules that I tell here. But as a best practice, you do not have to store the age, and because you can just always compute it. And there is a data security field that is protected, as you can see, and it may have to be modified by subclasses if they add some further attributes. And we also want to store the first names. There is at least one of it, and order is important, and one name may appear at most once. So here is the signature of this operation. Last names, there is also at least one surname, and also the order is important. And the name is calculated from the first and last names, and for a name it cannot be always decided whether it is a first or last name, so it is a read only. And you can see that the multiplicity is at least 2, because the multiplicity of both the first names and last name was 1. And we can also store the addresses. So here you can see the personal addresses. Actually, any number of personal email addresses can be stored. That's why we used this star notation. And one address may appear only once here. And the corporate email addresses, actually, you can have also any number of corporate email addresses, and one address may appear only once. So it's unique. And it is a subset of the addresses. So the addresses is the union of the two above. And because for an address, it cannot be determined whether it is personal or corporate, thus it is read only. And we saw the attributes, but as I mentioned earlier, we also define operations for our classes, for our object. And the definition of an operation is that an operation is a behavioral feature of a classifier that specifies the name, type, parameters, and constraints for invoking an associated behavior. And operations may have pre and post conditions. Have you ever heard about design contracts? Is there anybody who have heard about this concept? Okay. So a precondition of an operation defines the conditions that must be true when the operation is invoked. Otherwise, the operation, we cannot make sure that we can execute the operation. And the post condition of an operation defines the conditions that will be true when we completed the operation. So the precondition tells us how and under which circumstances we can invoke an operation, and if these circumstances, these conditions hold, that means, and we invoke the operation, then also the post conditions will be satisfied. Those constraints will be satisfied. And an operation may raise an exception during its invocation, and if an exception is raised, actually we cannot ensure that the post condition of the operation is satisfied. So with this exception, we indicate this fact. And the notation, the textual notation is based on this language, and we will go into the details. But we also have to emphasize here that the signal reception is also kind of behavior. It's a delayed operation triggered by a signal, and you can process these signals. You can receive the signals in, for example, activity diagrams, state machines. So let's see how it works in practice. We will have another example of a mathematical library. There will we have this add function that adds two numbers and returns this result, the sum function that receives a set of integers and returns their sum. We will define this floor function that receives a set of natural numbers, and for each number n, it changes to its nearest integer value that is not greater than n. And we will see also a Fibonacci function that returns the first n Fibonacci number, where n, the default value for n is 10. Here, what you will see is that the order of the numbers is important. The check Fibonacci will check whether an integer sequence is actually a Fibonacci sequence, and we will have also function, an operation to search for primes. So this primes function, primes operation will return the first n prime numbers, and it's important to know that primes are unique. So we will see how we can define operations, their visibility, name, return time, parameters, and properties. So here is the class diagram of our mathematical library. As you can see, the first function is to add two numbers, A and B, and it returns the result. The sum receives a set of integers and returns their sum. And the floor will receive a set of natural numbers, and for each number n, it changes to the nearest integer. So here you can see the multiplicity represented by star, and it's an in-out parameter. Can you tell me what is the problem with this function? Logically, so it's very easy to answer. So the definition is actually bad because we will just give natural numbers, so we don't have to do anything with them because you know, natural numbers, if you just compute their floor, it will be the same. Okay, but it's not important from the UML point of view. I was just curious if you still pay attention or some people have already fallen asleep. And as I mentioned you, we also compute Fibonacci numbers. So this operation returns the first n Fibonacci number where the order is important, and you can see that we defined the default value to 10. And here you can see that it is ordered. Check Fibonacci checks whether an integer sequence is actually a Fibonacci sequence. So it will return a Boolean value, and it receives some integers. And primes, operation prime will return the first n prime numbers. And it is important to know that primes are unique, and we can also indicate it here in the signature of this operation. So now we are able to define various classifiers, their attributes, their operations, but we also need to define relationships between classifiers. So what kind of relations we will touch now? We'll start with generalization. When a classifier is derived from another classifier, it is also called subclassing or extending or inheritance. And we will also use associations that defines that the instances of the classes are connected somehow. So it mainly depends on the implementation, how it works in your system. It can be implemented by pointers, by references, and so on. And we will also see dependencies that represent an informal dependence of a class on another one. So the definition of association is the following. An association describes a set of tuples whose value refer to typed instances. And instance of an association will be called a link. So in the formal way, it is to represent relations, formal relations between our objects in our system. And an association specifies a semantic relationship that can occur between typed instances, and it has at least two ends represented by properties, each of which is connected to the type of the end. And more than one end of the association may have the same type. So here you can see the notation, the name of the association, the roles, the multiplicity, and actually the classes at the end. So the name is the name of the association, and the role is the name of the association end. So it defines how these classes can see each other. And also the associations can have visibility that are actually, we use the same notation as before, so they can be public, private, protected, or package. And their multiplicity that is defined in the end, it can be exactly 1, exactly n, between n and m, or it can be any. So with the help of this notation, we can define the associations. And the number of the associated classifiers is called the arity. It is typically 2. So here is, you can see we have 2 and, but theoretically it can be any. So we can consider and we can build actually hypergraphs from by using these associations. So for example, the car, the ownership of a car is a binary relation. But for example, the parenthood is a ternary because it is between person, person, and person types. But there can be even for area, for example, the production, when we have model, designer, manufacturer, and tester classes. And number and the associations have their multiplicity at the end, and it can be an exact number, interval, or any. And for example, in the ownership, there can be a single person can have many cars. So one person can have any cars. But for example, the parenthood is just one person with one other person, and they can have any children. So the mother, father, and their children. So you can use multiplicity for this purpose. And you can also navigate through the associations. So the instances of the classes of the classifiers can access each other at runtime. For example, in a purchase, a customer can access the shop. But for example, this is not true for the other direction. And there is a special kind of, there are special kinds of associations, and we can use aggregation kinds that will model some whole part relationships. So it can be that we don't want to model whole part, so there is no aggregation, for example, for a car and a person. It can be, we can use shared aggregation, for example, between a car and the wheel, because the wheels can be standalone products, but they are actually the car is composed of wheels amongst others. So it's kind of shared aggregation. And the composition is, for example, between the tree and the branch. So especially if we say that there are no branches without trees, and that's more or less true, because without trees you will not get branches. And it is a strong form of aggregation. That means that the part instance, so a branch, is included in exactly one composite at a time. So a branch will be part of the tree. And if a composite is deleted, all of its parts are normally deleted with it. So we just kill the tree. It will definitely, unfortunately, kill its branches too. And as I mentioned, you can navigate through the associations, and you can use this binary association to represent the binary associations. And if you want to represent an n-ary association, you will use this diamond notation. So for example, this ternary relationship where there is one mother, one father, and they can have an arbitrary number of children. And let's see a more complex example. A car ownership example. So here is the car, the person, and this is the car ownership association. Here you can see the role of the class in this association. Here is the person in this association, and the cars. And the multiplicity is represented by star, because we said that a person could have an arbitrary number of cars. And as you can see, here we have an operation, and we want to calculate the taxes that this person has to pay. And it depends on his cars. So for example, at runtime, this calculate tax function can access the cars and access the calculate tax function for each cars. So it just has to collect all the taxes of the cars and sum them up. And if we extend with some composition, here you can see that the car consists of at least 4 wheels and an engine, and no cars can exist without these parts. So the cars must have these wheels and an engine. And you can see this arrow at the end. This means that it is navigable only in a single direction. So for a car, we can easily collect its wheels and the properties of its wheels, but a wheel cannot really decide and know which car just composed of it. And on the other side, on the other hand, here you do not see these arrows. That means that both ends are navigable. So for a car, we will know the person, the holder, and also we will know the person's cars. So it is represented by not using these arrows at the end. And I mentioned you this generalization so many times, so we will now formally define generalization. Generalization is a binary relationship. Namely, a generalization is a taxonomic relationship between a more general classifier, that is the parent, and a more specific classifier. And this means that each instance of the specific classifier is also an indirect instance of the general classifier. And the specific classifier inherits the features of the more general one. And any constraints that are applied to the general classifier also applies to the specific one. So just to see an example, we have sensors that measure physical parameters of environment, and sensors are characterized by their accuracy. And we will use special sensors in our system, namely a speed sensor and an acceleration sensor. And we will have also cost-efficient integrated device that will combine the speed and the acceleration sensor in a single device. So we will have two specific sensors, one for measuring the speed, and the other sensor is to measure the acceleration. And as I told you, both of them are sensor. So they are both inherited from this sensor type. And they will both inherit the accuracy attribute of sensors. So this way, we could, how to say, abstract and categorize our information. We can say that we can just raise the abstraction by telling that this sensor type is describes many concepts in our system, and we can reuse the information that and extend the information that we defined in our sensor data type. And as I mentioned you, we have a special sensor in our system that is the combined sensor that will have the properties of the speed sensor and the acceleration sensor, and it can provide us the same services as both together. My question is, what is the accuracy of the combined sensor? So it's very difficult to tell, because actually that can be that it just inherited one accuracy value, or we can just tell that we will copy both accuracy values. With this diamond form, we usually want to avoid this kind of inheritance, because that's sometimes very ambiguous. So be careful when you use inheritance, and please avoid this kind of diamond forms. Actually, there are some programming languages that in where it is prohibited because of this reason, because of this ambiguity. So it's very easy to make mistakes. So now you could see how inheritance and generalization works. But I will just tell you some words about how you can imagine it as a mathematical concept. So we have the sensors. The sensors is a huge set with all the sensors in the world. And in this huge set, with this inheritance, we will just define a subset of sensors that are the acceleration sensors, and we will define another subset in this huge set in the universe. In this subset will be the speed sensor. So in the mathematical sense, when you define inheritance and generalization, these classes can be regarded as I formerly mentioned, these are sets, they represent sets of objects. And this way we can tell that this is the objects that are the instances of this class. Actually, all these objects, they represent, they consist a subset of this more general concept above. And actually, I also want to tell you that here, the sensor class is abstract. That it means that you cannot instantiate, you cannot have direct instances of this class, because there are no sensors in the world, only speed sensors, acceleration sensors, and all the other sensors that are inherited from it. So if you define a class as an abstract class, and you cannot instantiate it. It is just to to represent some the information and the concepts in a hierarchical way. Okay. Is it clear? Okay, I hope so. But if you have any question, please ask me, because I can talk a lot, but I'm not here to talk a lot. I'm here to put this knowledge into your head. So please ask. So, and we can extend the generalization into generalization sets that are actually defined as a generalization set defines a collection of generalization relationships with the indication of various taxonomical concerns. So these generalization sets can be viewed from the completeness point of view. So whether subclasses cover all instances of the supertype. Here we have the possibilities of completeness and incomplete. And also we can consider the overlapping of the subclasses. So whether an instance may belong to more than one subclass. And they can be disjoint or overlapping. And I will just show them in an example. So here we have the specification that people are either male or female. Sorry, this is a quite old slide, so nowadays this is not completely true, and sorry for that, but please use these concepts just now for the example. So, and we say that there are no other genders. And this way we can say that if a person can be male or female, this representation is disjoint. Okay, sometimes this is also not true nowadays. Sorry for that. But complete, because these two sets cover all the person, all the people in the world. But if we just extend it with children, then it is not disjoint anymore, because a child can be male, female. So it will be a overlapping, but it is still complete, because we cover all the person, all the people in the world. And here you can see another example where with trees. So we have the abstract concept of tree, and trees can be apple tree, pear tree, and pine tree. And there can be actually also other kind of trees in the world, especially in Brazil. I was in the jungle and I couldn't find two trees from the same species. So here this is absolutely, how to say, under approximation, but you can find here. It is disjoint but incomplete. And we want to also categorize people. So a person can be a salesperson or a manager. But actually, there are salesperson. There can be salesperson that is also a manager. So it is overlapping and it is incomplete because, for example, we engineers are not represented here. And we are a very important class in the set of people. And I will also show you another example of the associations. So the specifications is the following: vehicles are owned by people, and the special kind of vehicle is a car, and the special kind of a person is a car owner, and the cars are owned by car owners. And this is a special kind of vehicle ownership. So we will show now the generalization between associations, but this is a very weird example, and it aims only the demonstration of a rarely used feature. So you can also define a generalization between association, but please try to avoid it. Okay, and now we will have, you have to work now. So I have some examples, and you have to decide if it is an instantiation or inheritance. So I suggest you to have, let's say, 2 minutes, and I will ask you to think about it, and then I will ask you about your opinion. So that you have 2 minutes for that. Could you agree on a solution? I see that you in the front, you talked a lot about it. I'm sure that you have the perfect solution. Can you help me? So the first one, Fifi is a poodle. So what is this? Is it instantiation or inheritance? Yeah. This is instantiation. Okay. Poodle is a dog. Yeah, this is inheritance. Dog is an animal. Inheritance. Poodle is a breed. Yeah, this is instantiation. And dog is a species. This is closer to instantiation. So if you, so when you try to decide if something is instantiation or inheritance, you have to ask a question: Is one is the subset of the other, or is one is the element of the other? So in instantiation, you will get that this is an element of a subset. In the case of inheritance, you can say that this is a subset of the other. So this is how it's a little bit easier to answer these questions. But you are very, very good. So I'm happy because you pay attention. Yesterday you were really passive, and I was afraid of losing you. Okay, we have a couple of slides about some other stuff. UML, so dependency is a general relationship that signifies that a single or set of model elements requires other model elements for their specification or implementations. And actually, this dependency is not how to say too formal relationship. So it can nearly mean anything. And the dependencies are shown by a dashed arrow between two model elements. You can see the example here in our program. The shape depends on the drawing context, but we do not know how and why. It is used to indicate that if you modify, for example, the implementation of the specification of one class, you have to be careful and have to take care about the other class too. And we also have to formally specify enumerations. An enumeration is a data type whose values are enumerated in the model as enumeration literals. And an enumeration literal is a user-defined data value for an enumeration. And the semantics is that the runtime instances of an enumeration are the data values, and each such value corresponds to exactly one enumeration literal. And we will use the classifier notation. So with this enumeration keyword, and here you just have the list of enumeration literals. For example, in our case, for name prefixes, Mr., Mrs., and so on and so on. And there are other structural diagrams in the UML. Component diagrams represent components and their internal structure modeled as components. So they represent the main system components and their relations. The composite structure represents the internal structure of the components and the collaborations. And here you can see an example component diagram. And also UML provides deployment diagrams, but this is not the strength of UML. So we will see in the next presentation of SysML that it provides much better languages and support to represent deployment. Okay, do you need break? How much? 15? Do you want to stay here until 7 o'clock? 10 minutes. Okay, please come back in 10 minutes because we have so many materials for today, and I don't want to make you stay here at night.